Good morning, everybody. My name is Major Robert Fusco. I'm a current MOVE student graduating in June. Today, I'll be presenting my thesis research, Marine Corps Recruiting Artificial Intelligence Generation Engine, or MCRAGE. The agenda for today is separated into 7 sections. We'll go through the problem statement, the background, the resulting MCRAGE trust framework, the output agentic hybrid RAG architecture that came from this research, some more results, and then some recent expanded work, leaving some time in the breakout rooms following the session for discussion. The main research question we sought to answer with this research was, can an implementation guide or framework be developed for applying large language models and RAG architectures to build AI-powered decision enhancement tools grounded in doctrinal military planning processes? Additionally, can we demonstrate this in a time-sensitive and relevant operational context, such as Marine Corps Recruiting Command's Command Group Action Plan process? So this is a real gap at Marine Corps Recruiting Command. They have one of the most non-kinetic consequential missions in the Corps. Specifically non-prior service enlisted accessions. They do not currently have dedicated modeling and simulation support, despite operating in conditions that meet every classical wargaming criteria: adversarial, uncertain, and time-sensitive. They have the data, they have the doctrine. Right now, they don't talk to each other without manual human inputs and legacy planning sessions. Commanders at the tactical level are making decisions against disaggregated performance data, along with their natural language doctrine and orders. There's no unified tools or traceable recommendations, and no decision support at the speed of their decision making. Implementing such a solution set is a hard problem for the purpose of trust. AI adoption in operational military environments fails without explainability. I know the vast majority of the crowd is technical in nature, but for those who are dialing in who are not, this is meant to be a brief primer on about 2 years of AI classes down into one slide. On the left-hand slide, you see the hierarchy of artificial intelligence, the overarching bubble that we define as AI. Inside of it, you have the first nesting doll, machine learning. You can think of that as data in machines where patterns are learned over that data. Deep learning then takes those pattern recognition and places them into what we call neural networks or deep neural networks that really you can think about as a model of the human brain, just in a digital form. Then there is generative AI, which is taking those neural networks and producing new content out of them, whether that's audio, text, or video. And then kind of at the center of this nesting doll is what most people, when they think of AI, what we're talking about is large language models, which is generative AI predicated on natural language. In the middle, you'll see a moving diagram here. That is the transformer architecture. This is the underlying technology that underpins all modern LLMs, coming out of a 2017 Google DeepMind research effort called Attention is All You Need. That's kind of the quintessential paper in this field. And really, this is about a 30-second spiel about how LLMs work, so I'm going to try to breeze through this. At the top, you have your inputs. That's natural language. That's what you type into a prompt or speak into your microphone that gets converted into text. That textual natural language inputs gets broken down to what are called tokens. You can think of tokens as bite-sized chunks of words and overlapping words. Each one of those, the system gives it a positional embedding. That is its location in your input. And then it goes through this decoder block in the middle. You can think of this decoder block as one big pile of matrix math or linear algebra. We're not going to get into the details, but the important piece about the transformer architecture is called the attention block. You'll see that noted as the green masked attention layer. What that does is each input gets from its positional embedding, how important it is based on the training data, so the corpus of natural language it was trained on, what each word or part of a word, how important it is to the other ones in that order. Some normalization occurs, it gets put through a feed-forward neural network, and then tokens get outputted. The end state is the system takes your natural language input, and then all it's doing recursively is it's finding what it thinks is the most likely next token with a little bit of randomness in there. So it gives new results every time. And then it predicts a sentence over time. And because of the training data, it looks and acts a lot like human thought and human language in the end, because that's what it's trained to do. The strengths of a system like this, great at summarization, and it's great at pattern detection because of the large corpus of natural language it's already trained on. As an extension of that, it's very good at natural language reasoning, because if you do this again and again and have the model talk to itself, you get what's called chain of thought. It's great at domain translation, so bridging disaggregated and different types of text and data together in kind of a human synthesis. And this is really the bottleneck we're going after with this architecture. The weaknesses, though, and this is what the research had to overcome, is that there's no structured grounding. You'll get confident wrong answers from an LLM because it's just predicting the next word. Additionally, you can get context overload or drift, and that because of that tension mechanism in the middle, it's going to focus in on parts, and when you have a large input of data coming in, it will lose context, and that's compounded by the probabilistic nature of how neural networks work. The third is that it can't do math directly. So it's weak on numerical precision, time series comparisons, and anything beyond a simple single calculation. That's because it hasn't seen it before. So it's relying on chain of thought to predict tokens and not actually do the math. And then the final one is the most dangerous one. A lot of people say you can overcome all of these with prompt engineering. That's not a true statement because schema non-compliance happens. And that's when the system produces a logically coherent output, but that's invalid for what a human would actually reason out. Our approach to address these difficulties is the MCRAGE trust framework. And the idea here is that to use an AI system for operationally relevant planning purposes, you need to build trust and it can't be assumed. So we seek to implement full traceability across all data and all outputs, enabling marine trust in the system. To do that, we have a little MQ9 clip art here. And just like on the MQ9, we have some hard points that we're going to hang features off of. And I call these are our pillars that how we're going to reach trust. The first one is hard point 1, and that's semantic modeling. Large language models are trained in natural language, mostly English based on internet data. So we're going to speak in the model's actual language to it. We're going to communicate in natural language back to the LLM to make sure they can reason over what it can naturally read. Hard point 2 is context curation. The idea here is we're going to feed targeted packages of information to the model, not all the info at the same time. That way the model's getting a signal to reason off of and never a bunch of noise along the side of it. Hard point 3 is hybrid architectures, and this is analogous to the MAGTAF. You wouldn't send the LCE to be in your main effort in a ground fight, just like you wouldn't let the ACE be the main effort in a logistics battle. So things of that like, so we're going to use focused agentic efforts on that. And so we're going to find the right tool for the right problem every time we ask the model to do something. And then the fourth and the most important one is traceability. The number one complaint with AI systems is you're not able to backtrack into them. They're black boxes. So we have to find a way for the model to show its work. And we do that with every claim and output is traced back to a source with reasoning steps that are auditable by humans in order to build that trust. This is what it turns into once we put it into a system architecture. So on the far left, you have data sources. This can range from anything from operational databases. In MCRIC's case, this is MCRIS, the Marine Corps Recruiting Information Support System. You have policy, doctrine, and SOPs, and those are text-based documents with some tables in them, mostly PDFs, Word documents, TXT documents. And then you have historical records, which could be a mix of audio recordings, PDFs, handwritten notes, really anything that augments what's in the database and what's in policy. Then we move to hard point 1. So we're going to ingest and represent this data. Anything that's structured, and you can think of that as tabular data or metrics, we're going to put them into a knowledge graph. In this knowledge graph, we're going to go from tables, so rows and columns, and we're going to do a semantically modeled graph with human readable edges in between nodes that define relationships and what's inside the node. For unstructured, that text-based data, we're actually going to put it into a vector database. And for the purpose of this, you can think of a vector database as a multi-dimensional spreadsheet. We move into then hard point 2, which is query and decompose. The operator using the system is going to ask a natural language question, which is going to be passed to the first agent, which is a decomposition agent. And that agent's job is to take out all the key points from the question and then route the question either to a data agent or a policy or doctrine agent, or to both agents simultaneously. The idea here is we're picking up the signal immediately. What are we talking about and what type of data is it? And what tool do I need to do the job? So that's the signal, not noise part. The hybrid reasoning is each one of those agents has a different role. The data agent's going to handle graph queries, metrics, and then source attribution. What does the data say is the question it's going to go after. The doctrine agent or the policy agent is going to do a vector search on that vector database we talked about and pull out cited policy passages in the form of chunks. So what does doctrine or policy say about this question? They both get fed to a supervisor agent that fuses them. It flags any conflicts, and then it presents a full reasoning chain for output. That hard point 4 is the trust gate and output. This is the verification step. So every claim is going to cite a source. So we're going to see the graph nodes and the relationships. We're going to see the document paragraphs or the initial data record that was used for the agent and the models to reason off of. And that this whole approach is schema validated. So it has some guardrails that it doesn't allow it to leave what we tell it should be reasoning off of. And that the end state there is a reasoning chain is fully visible. And then the last part's the most important part. This whole system seeks to enhance human decisions, not replace them. We have humans always make the end call. It allows the human to see what the model said, its recommendations, where it got the data from, but allows the human to inspect them before any decisions are made. In the context of Marine Corps Recruiting Command and MCRAGE, this is what that architecture turns into. And this is just a flow chart that goes from the user question at the top. It enters that query decomposition we talked about. That decomposing agent enters a route decision. So on the left, it can go to the doctrine agent, where it runs through that pathway. The middle is the data agent pathway. You'll see in the middle there that you have the large language model actually generate the graph database queries that pulls the data. And then on the right-hand side, you have the mixed query. And the important part about this is both agents run in parallel, the doctrine agent and the graph agent. It gets passed to that merge supervisor agent that synthesizes both for a final answer. On the far right in the bottom, you have the automated analytics pipeline. And this is everything we added over the top. So you can think of this as read-ahead generators that take a set of commonly asked questions for the planning process and generate responses ahead of time into a pre-formatted document. We additionally included some foundational models that have recently come out. Amazon Chronos 2 is a time series forecast model that runs over the top of a graph database and will do risk analysis. It's meant for financial decision making. However, we applied it in this case to contracting decision making for Marine Corps Recruiting Command to give a risk read ahead, more or less, for every CGAP meeting. And these get consolidated into pre-built reports that can be accessed through the user interface. So this is the first results, and this is the MCRAGE specific slide. So this is the data we had coming in and what it ended up being in terms of our MCRAGE system at the end. On the top left here, box number 1 is the MCRAGE MUD file. So this is what defines the recruiting area of operation and the territory boundaries. We were looking at 42,000 odd zip codes, and then we're mapping each zip code to a FIP code, which you can think of as a county code for the post office, a state, the actual county, lat long, the status, and the current organization it belongs to. Then you have the MCRAGE organizational file. This is MCRAGE's COMREL. It denotes the headquarters going down to regions, then districts, recruiting station, that's our focus of effort, and then the recruiting substations, the subordinate units that each recruiting station owns. This has the names of the units, the short names, their shorthand abbreviations, their numeric identifiers, street, city, state, the MEPS, or the entrance processing station that each RS is assigned to, and then the status. Is it open? Is it closed? Is it going through something right now? And then the third is the propensity file. So this is the forward-looking data that MCRAGE has, separated into a couple bins. QEP, which is a proprietary metric, CNIP, which is civilian non-institutionalized population, and MHSSR, which is a military health system recruiter survey. And those are outward projections from 2025 to 2045 by zip code and organizational ID that talks about the recruiting population in that area in the future. You can think of that as an intelligence report, an intelligence database. For number 4, that's the activity and performance data, what was actually done. This was captured at the RSS level, and this is both mission and achievement data. What were you tasked with? What did you actually achieve? 57 metrics per RSS per month were captured this way across both achievements and mission. So really combined math and public here, that's 114 metrics per month per RSS. Those were all statically polled in the middle of September. And then we anonymized the data further. So everything was already aggregated to avoid PII. We took it a step further, is we took RS Raleigh and then we placed it into a synthetic environment, RS Anytown. So those are real operational metrics, but now we're in a training environment, and that further sanitizes any PII and kind of NPS IRB requirements. Then the final piece, number 5 on the right, is unstructured data. So this is all the doctrine that's listed there from MCRAGE, as well as trip reports, which are the command group when they go out and visit a recruiting substation. This is their kind of output trip report. Those get fed into that vector database at the bottom. And then numbers 1 through 4 get fed into the Neo4j graph database. The results here is that we semantically model the schema. So this is what the graph database actually looks like. And the key takeaways from this is you see the hierarchy, you see the recruiting station, it pops up there. Then you can see an edge that goes to the recruiting substation, has substation. Those are in plain English. That recruiting substation has zip codes through a located edge, and then it has a monthly report hub, which you can think of as the main organizational hub for all the data that it's going through right now. But the key takeaways on this slide and this kind of rotating chart we have is that every node has a plain language label, and that every edge also has one. So the model, when it queries, is talking in natural language. You can see at the far right what it's going through now is the document and chunks. So these are where we take that vector database and all the trip reports, and then we bring them back into Neo4j so we can use one consolidated query that the LLM can write itself. What does it actually look like? So this is the user interface for MCRAGE. This was at the end of MVP2. Pretty standard AI interface, LLM interface, acts a lot like ChatGPT. System status is on the left, the models it's connected to, the databases it's connected to. The first question we gave it, it gets routed to an agent. You can see it was decomposed. The right agent was picked. Now final inference is happening. So this is a doctrine question. It asked about the command group action plan. What is it? What are we actually doing here? You can see that it gives out an explanation. It ties back to actual figures and pages in the doctrine and the traceability there. I could go to volume 3, open up the PDF right now, go to page 104 and find where it got information from. At the bottom, there were additionally stats. The next question we have is a data question. So that gets routed to the Cypher agent that writes the query. That's in green in the middle. So that's what the LLM actually came up with. The answer above it is the output from the graph. And you can see this one moves very fast through the graph. We additionally have a diagram that shows that routing visually for the user to inspect. And the last one, we're going to ask a mixed question here. So this one takes a little longer because it's going to, in parallel, hit the doctrine agent and the graph agent. Our target for all these queries in aggregate across over 1,000 queries was under 7 seconds. We got it down to 6.7 seconds average. This was one of the longer questions. So conducting final inference, hit it right about 20 seconds. So this is the role of the sergeant major. Same thing, reading through this, what his or her responsibilities are at the recruiting station. And then a completely separate question that's not related that the graph agent had to query through is that's a future-looking projection for a specific metric in 2040. Pulled it out, all the RSSs are there. Then we get down at the bottom, it gives the mixed traceability. Where did it pull the doctrine from with page numbers? And what graph query did the LLM actually write to get that CNIP data that it gave at the top? Once again, has a diagram of where it pulled the data from, and then the performance metrics at the bottom. You have some basic clear chat, save history, clear history, and that's really it for the user interface. This is the work we expanded to after we got the user interface up and running and ran all the results and benchmark testing on it. The first one we did was for the MCRAGE National Structure Working Group. The Commanding General of Marine Corps Recruiting Command had an RFI of what would their structure and force laydown look like if it was assembled AI absent of human involvement. So a clean slate, what would AI structure MCRAGE have for mission success? To do this, we expanded on the graph database, and then over the top of it, we ran what's called a graphical neural network, or GNN. The other way to phrase that is a GAT. So that GAT informed 5 state-of-the-art large language models that were assembled in a council so they could talk to each other. And they each developed, across the 5 of them, 200 optimization strategies. We then solved those optimization strategies with GPU-accelerated tools, specifically NVIDIA QOpt. Then we re-met the council with those results, and they evaluated a best structure without a human in the loop. This took about 6 months of legacy OR and staff work, and compressed it down into 4 days. About 1 hour each day is what I spent on it. This was briefed back in March to MCRAGE at the NSWG. The interesting part about this is it largely validated their current structure, which was exciting for me because I know how hard the guys work there, and they did a great job. Now, hopefully they can use tools like this just to speed up their process and get even better. On the right here, the next video is integration with Apple Vision Pro and augmented reality. Really the target here was, what does advanced data visualization techniques in an augmented reality field get us? Can we present the same LLM decision-making tools in an augmented reality space where decision makers can visually see and inspect the data, the outputs in their real-world space while they're making decisions? This video's in my garage, so it's a little dark, but you can see the Neo4j graph schema that you saw is actually presented in 3 dimensions in augmented reality. You could walk around it if you want to. You could pull the nodes. We additionally added voice to text, so you can plain language speak your question in there, submit it to the model for reasoning off of. So that was a cool little experiment we had. And then the final piece we really did was integration with GenAI.mil. So I was a beta tester in February and March for the first API rollout of GenAI.mil. To my knowledge, we are the first government system that was successfully connected and ran on GenAI.mil infrastructure. So we ran the full MCRAGE stack across Gemini 2.5 Flash and Gemini 2.5 Full. And this served as a future proof of concept for rapid integration of agentic AI use cases into DOW programs of record. Pending any questions and comments, there'll be a breakout room following this. My contact information is on this slide. Additionally, of note, on June 19, one day after graduation, I will be staying around here with the Deputy Commandant for Information and the Service Data Office. We are standing up the Marine Corps Digital Transformation Accelerator here at Naval Postgraduate School with the target of further integrating artificial intelligence efforts from both the academic and the FMF side together into some synergy. Thank you for your time this morning.
Hello, my name is Captain Josh Lampe, United States Marine Corps. I'm here to talk to you today about my research into developing a framework applying multiple simulations in a training progression specifically related to marksmanship. So the agenda for today, we'll briefly go through the problem statement, the background, and then go into the approach, results, and future work, and then lead into any discussion after. The problem statement: simulation-based training systems that support the same competency are often used independently without a standardized methodology for sequencing and combining them throughout a training progression. Essentially, there are a lot of great training simulators, training aids throughout the military and the Marine Corps specifically, but there is no documentation into how to actually utilize them within a training progression. They're all analyzed as a standalone system. For this research, marksmanship was used as the case study with the 2 listed simulations or training aids. The Advanced Small Arms Lethality Trainer, which is largely here to replace the ISMIT, the Indoor Simulated Marksmanship Trainer, and the Joint Marksmanship Assessment Package, JMAP. JMAP is really just an electronic scorecard that's paired up with a live fire course of fire, but I'll refer to it as a simulation for the purpose of this study, either a simulation or a training aid. For background, this research originated in the Commanding General of Training Command, identifying a need and understanding the role of the 2 marksmanship simulators in a training progression. Essentially, we have both of them now. They are very useful and beneficial, but there is no standardized documentation or research into when we should use one over the other in a training progression and what one brings that another lacks, or one's strengths and limitations compared to the other relative to a training progression. Further, in the research, there was actually no studies directly addressing utilizing a combination of simulations in a training progression. Most research dealt with training transfer, seeing if training in a simulation transferred to live application, just evaluating individual simulators to see what their strengths and limitations are, or comparing multiple simulations just to show that one may be beneficial in one application and another beneficial in another application, but not actually showing where they would fit inside of a training progression. So going into the approach, the first step was to develop the actual framework. So it looks like the 9 steps laid out on the PowerPoint right now. So to define the task, decompose the task into performance steps, classify KSAs, identify appropriate performance measures, define proficiency levels, identify affordances and cues required, align performance measures with the appropriate proficiency level, evaluate simulator capability, and align simulator capability with affordances, cues, and performance measures. Something to note, steps 1 through 7 deal specifically with the competency itself, and you don't compare them to the simulator until steps 8 and 9. And this is to ensure an independent and objective analysis of the actual task and not introduce any bias from the simulator by looking at it too early. So next we will apply this to marksmanship and walk through the purpose of each step. So step 1 is define the task. This task was taken from the Marine Corps Infantry TNR manual, Training and Readiness manual, which was engage targets with a service rifle. Step 2, decompose the task into performance steps. This was also taken from the TNR manual, and you'll notice number 6, engage the target, is highlighted. That is what we will be using specifically for this application. Step 3, classify KSAs. For engage the target, we're looking at muscle memory and intuition as the types of KSAs that we are evaluating. And the purpose of step 3 is more to inform step 4, which was identify appropriate performance measures. It's not to limit it specifically to these types of KSAs, but to lead into the following step. Step 4 is identify appropriate performance measures. The actual list is omitted from this just based off length, but the intent of step 4 is to have a repository of performance steps and definitions to be able to pull from later rather than trying to think of them as you go through each proficiency level. This just mitigates forgetting one later on or just not having a complete list of proficiency measures. Step 5 is define proficiency level. So for this, we used the Dreyfus model of skill acquisition, so novice to expert. And the example that I will walk through is the advanced beginner example. So the proficiency level, advanced beginner, definition for it is engages obvious threats after delay inaccurately and needs guidance. Step 6, identify affordances and cues required. So you'll see next to the definition, all the affordances, which is what I need the shooter to be able to do at this proficiency level. You'll see affordances, which is what I need the shooter to be able to execute at this proficiency level. And cues, which is what I need the environment to provide for the shooter at this proficiency level. Step 7, align performance measures with appropriate proficiency level. So this is going back to our list from step 4 and listing out all the performance measures that we'll need at this level. Again, you may use some performance measures from step 4 multiple times. You may never use some performance measures that you identified in step 4, but you have the bank to pull from as opposed to trying to come up with these during the analysis. So this figure on the right-hand side shows steps 5 through 7, which again, this is done completely independent of any sort of simulator analysis in order to ensure that we are analyzing the task correctly before applying any simulator capabilities to it. This figure now shows what happens during steps 8 and 9 of evaluating the simulator capability and aligning that simulator capability with the affordances, cues, and performance measures identified. So anything green with a Y is noted as the simulator or simulated environment fully offers this capability. Anything yellow with a P indicates the simulator or simulated environment partially offers this capability, or just requires extra analysis in order to determine the performance measure and evaluate the performance measure. Anything red with an N indicates the simulator or simulated environment does not offer this capability or a way to evaluate this performance measure. And anything blue with an O indicates that the simulator or environment does not offer this, but it's easily observable by a trainer or a coach. You'll see next to affordances, cues, and performance measures, one column for ASALT, one column for JMAP, showing the alignment of the simulator capability with that affordance, cue, or performance measure. And then next to that, comments, because green, yellow, red, and blue do not paint the full picture. So the comments basically explain anything that's not fully offered or of note from your analysis. So for example, for the affordances, ASALT is marked partial for receive recoil because it only provides a limited recoil when firing the weapon. And you'll see that JMAP is marked partial for target size differences and target distance differences due to the reliance on available equipment, the range type, and targetry, and just that the simulation itself does not necessarily change this, and that it may require outside efforts from the training unit to support this. And then for performance measures, you'll notice that trigger control, breath control, and recoil management are all marked partial because there is no numeric value you'll get back, but analyzing the results can show indications if these fundamentals are not being employed correctly. Performance measures like muzzle movement and time to acquire target are marked no because there is no explicit way for either simulator to track this and identify either through a muzzle tracer feature or to identify when the shooter has actually sighted in on a target. While performance measures like follow through and stance stability are marked observable because, again, there's no numerical value that the simulator will give back, but a coach or trainer can observe the shooter in order to identify if they are performing this correctly. After conducting all that, an analysis of ASALT and JMAP was done, and this analysis was not meant to compare them yet, but just to analyze the alignment of the simulator capabilities with the affordances, cues, and performance measures. And from that, a recommendation was made. So for advanced beginner, at this stage in its training progression, a shooter is employing marksmanship fundamentals with decreased cognitive load. The shooter begins recognizing routines and patterns while employing the fundamentals, but errors are still high. Shooter is able to take on more challenging tasks, such as transitioning between two targets. So a medium physical fidelity simulator with detailed metrics and high functional fidelity was best. I recommend ASALT for an advanced beginner due to its functional fidelity. So this process was done for 5 proficiency levels: novice, advanced beginner, competent, proficient, and expert. And after each proficiency level, a survey was conducted with subject matter experts from Weapons Training Battalion. Essentially, the framework would be presented in its application to marksmanship. They would fill out survey questions, which we'll get into next, and there would be discussion based off anything they needed clarity on, or if they disagreed with some of the accuracy, or if they disagreed with any part of the presented framework. So on the left are all the questions that were asked for each proficiency level, and on the right, you'll see from left to right, top to bottom, the results for novice, advanced beginner, competent, proficient, and expert proficiency level responses. By and large, the responses were either neutral or positive. There are some questions where the responses were negative, but through the discussion and through the survey, important to note that the subject matter experts disagreed with maybe one component of the cues for a specific proficiency level, but agreed with the rest. But because they disagreed with that single component, they marked disagree for cues for that. But it was usually just one part of it and not the component in its entirety. For the overall framework, the questions on the left were asked with the results on the right. Again, the overall response was positive or neutral. So some key takeaways though from the framework application to marksmanship. Again, like I said, the disagreements focus mainly on specific elements, not the entire application for a given proficiency level. One thing that was debated was how JMAP affordances were represented. For example, for target size differences, because JMAP is just a electronic scorecard that is used during live fire, changing the target size, JMAP supports it, but the actual targetry is outside of the scope of the training aid. So there was debate onto how to properly represent those affordances with no clear consensus coming out of it. And then sequential versus simultaneous execution. So oftentimes the subject matter experts would evaluate the simulator capabilities at the same time that they were aligning affordances, cues, and performance measures to each proficiency level. And this would cause confusion as to why some performance measures were included or affordances were included. But the intent of doing it sequentially and the importance is to ensure that an objective analysis of the task is done before looking at simulation capabilities in order to mitigate any biases. And as far as the overall framework, again, general positive responses toward utility. The subject matter experts thought that it could be useful for other marksmanship performance steps. One example would be firing at night and breaking that down into proficiency levels. And then it could possibly be useful for other competencies, such as driving, medical, fire support. So future research should include operational testing and evaluation to assess the framework's accuracy and utility in practical training environments as opposed to just a theoretical framework. Also, expanding the framework to either different weapons platforms, night operations, like I said earlier, or looking at other marksmanship simulations, whether they're commercial off the shelf or other programs of record, and then generalizability. So how does this framework apply to other competencies such as driving or fire support? That concludes my presentation. Thank you for listening. Please reach out if you have any questions. Thank you.
Good morning, everyone. My name is Major Amin. I'm currently a student at Naval Postgraduate School pursuing my master's degree in modeling simulations. I'm a Marine Corps officer and a logistics officer by trade. And this morning I will be discussing my thesis research, which involves developing a framework to guide the design of simulation information system training environments that support contested logistics staff decision making. So in these events, staffs have to make sustainment decisions while routes are threatened, capacity is limited, and demand changes during execution. Simulation system may create activity in that environment, but that activity only supports training if it becomes information the staff can use to assess the situation and adapt. My thesis develops a reusable framework for defining that training requirement before selecting or comparing the simulation tools. I demonstrate the framework through a transportation and distribution vignette, build a baseline simulation conceptual model, or SEM, and then I separate the problem into a physical distribution layer and a staff decision information layer. And then I apply that structure to two simulations that I use to assess that. The two simulations are going to be JCATs and VR forces. I'll use this agenda to walk through the thesis. I'll begin with the problem statement and the background, then explain the framework approach. From there, I'll summarize the results of applying the framework to JCATs and VR forces, and then close with future work and the main discussion takeaway. The thread through the brief is simple. Define the logistics training requirement first, then determine what the simulation can support, and what must also be added to create a usable staff decision cycle. So the problem my thesis addresses is a training design problem. So in contested logistics, the staff has to adjust while the events are unfolding. So routes may be threatened, transportation capacity may change, and demand from supported units may shift. For the training to be useful, the staff needs more than just activity on the map. They need to understand request statuses, the backlog of requests, the priority of service requests, the resources availability, the route status to travel to and from our logistics unit to the supported unit, and the performance feedback to understand how the logistics system is working. So constructed simulations can help represent logistics execution in that environment. They can show units moving, trucks traveling along routes, disruptions occurring, whether it is contested route or due to obstacles or enemy actions, and also missions succeeding or failing. But representation alone does not necessarily facilitate the staff-facing information flow needed for that decision making. So the question is not simply, can the simulation move trucks? The better question is, can the training environment produce the information and feedback the staff needs to understand the situation and adapt to it? This is the research problem. Exercise designers need a repeatable way to define the logistics process and required staff feedback first, then compare candidate simulations against that requirement. The background for this thesis starts with the contested logistics doctrine. In a contested environment, logistics is not a fixed plan that simply gets executed. Routes can be delayed or denied, transportation capacity can change, supplies can be consumed faster than expected, and supported unit demand can shift during execution. So that means the logistics staff has to keep assessing the system and adjusting the concept of support. So Marine Corps doctrine and any military doctrine, that's concentrated on logistics talks about this in terms of logistics visibility and adjustment. So the staff needs visibility of demand. They need the visibility of supplies on hand, the readiness of all their assets and the infrastructure, and the throughput so they can make decisions about the priorities, the tasks, and the resources. For training, that creates a specific requirement, meaning the event has to give the staff enough information to understand whether the distribution system is working. This is where simulation systems become useful, but also where the design problem with pairs. A constructive simulation may know where the trucks are, what supplies are moved, what route has been delayed, or what mission has succeeded or failed. But unless that information is organized and presented to logistics staff in a usable way, it may stay as a simulation ground truth instead of becoming training feedback. So the background for my thesis is this connection between physical logistics activity, staff-facing information, and staff decision-making. My work uses simulation conceptual modeling to define the connection before comparing the simulation tools. The point is to identify what the training environment must represent and what the staff must be able to see. Again, not whether the simulation can create activity on the map. So for the approach, my approach was to start with the training requirement before comparing the simulation tools. So the framework begins with the intended use, which in this thesis is contested logistics staff training with a transportation and distribution focus. From here, I bounded the problem to a specific training vignette. A combat logistics company supporting infantry rifle companies with class 1, 3, and 5 supply requirements under contested conditions. That bounded vignette became the basis for a baseline simulation conceptual model. The baseline SEM identifies things like scope, entities, resources, behaviors, interactions, outputs, and assumptions needed for the training problem. The important point is that the baseline is not tied to JCATs, VR forces, or any other specific simulation tool. Rather, it describes what the training environment needs before a simulation is selected. I then decompose the baseline into two connected layers. The first is the physical distribution layer, which includes the network structure, the flows, capacities, route options, frictions, and state variables. The second is the staff decision and information layer, which includes what the staff observes, how they assess performance, what decisions they make, and how feedback supports the next decision cycle. Once those layers were defined, I used them to assess simulation fitness. The assessment asks what the simulation can represent, what the staff can observe, what the staff can change, and what must be added through a response cell, tracking mechanism, scripting, or some type of information system. In short, the approach turns a broad training problem into a traceable comparison structure. The results that stemmed from my evaluation of these simulation systems against the baseline SEM showed somewhat of a consistent pattern. Both JCATs and VR forces can contribute to the transportation vignette, but they are stronger on the physical execution side than on the staff-facing information side. For the physical distribution layer, both tools can help represent the activity that makes the event useful. They can represent the units, the vehicles, the routes, the movement, the disruption, and mission outcomes. JCATS provides a stronger physical logistics basis because it can more directly represent supply nodes, a more detailed inventory, more types of distribution vehicles, the route movement. They can define the state of vehicle losses and mission outcomes. VR forces can also support the scenario, especially through entity movement, route effects, object status, scenario events, and scripted disruption. But it requires more deliberate exercise design to build the logistics workflow around those actions. The larger gap appears in the staff decision and information layer. For both simulations, request management and performance feedback are the clearest limitations. Neither simulation tools by itself gives the staff a complete logistics workflow for generating, queuing, categorizing, prioritizing, and tracking support requests. Neither one automatically turns execution activity into the performance measures the staff needs, such as backlog of logistics requests, the response times to logistics requests, on the on-time delivery of missions. That does not mean the simulations are not useful. It means the training environment has to be designed deliberately. If the staff is expected to adapt the concept of support, then the exercise designer has to build the information layer that lets the staff see what is happening and judge whether the decision improved performance. That layer may come from a response cell, an external tracking, our scripted reporting, a metric aggregation, or a logistics information system. The main result is the framework made the missing design work feasible. It showed that the simulation activity does not automatically become decision-relevant feedback. So when it comes to future work, I think the future work should move this research from framework demonstration to a training environment implementation. So I'd say the first step is to broaden the framework beyond the transportation and distribution vignette used in this thesis. I thought transportation was a useful starting point because it includes like clear physical movement, capacity constraints, route choices, demand generation, and delivery outcomes. But the same approach should be applied to other logistics functions such as maintenance, casualty evacuation, engineering, supply, or any other type of broader sustainment problems. That would show which parts of the framework are reusable and which parts need to be adjusted for different logistics processes. A second area of future work can be to build the staff decision and information layer that this thesis identified as a major gap. The JCATS and VR forces assessments showed that the physical execution can often be represented, but the staff still needs organized information to manage requests, to track missions, monitor backlog of requests, understand the route statuses, and assess overall performance. Future work could build reusable staff-facing products using scripting, external tracking mechanisms, or integration with some type of logistics information system. The goal would be to translate the simulation state into the information the staff actually uses during execution. Another approach would be to test a framework in an actual training design effort. That would mean using the framework with a training audience, a response cell, simulation operators, or external displays or trackers, as well as an after-action review process. This would show whether the framework actually reduces ad hoc workarounds, improves exercise design, and gives staff more useful feedback during execution. So the next test is not just whether the framework looks good on paper. The next test is whether it helps a logistics staff see the system, make decisions, and adapt the concepts of support while the scenario is unfolding. So I just wanted to close out with this slide and a key takeaway from this thesis. I may have mentioned it already, but big takeaways, don't start with just a simulation tool by itself. Start with the decision cycle first. For logistics staff training, the question is not whether a constructed simulation can represent movement, routes, supplies, disruptions, or mission outcomes. Those things are important and they matter, but they're only useful for the staff training if they are turned into information the staff can observe, assess, and act upon. The framework helps make that distinction clear. It starts with the logistics training requirement. It asks what process the staff is supposed to exercise, what decisions they must make, and what information they need, and what feedback should show whether the decisions are working. The two-layer structure is the key idea. The physical distribution layer represents the logistics conditions. The staff decision and information layer turns those conditions into things, again, like request status, backlog, route status, resource status, and mission tracking, as well as the performance metrics. If the information layer is missing, the staff may be reacting to isolated exercise inputs rather than assessing the logistics system as it changes. So once the decision cycle is defined, we can determine what the simulation can support, what it cannot support, and what must be added through response cell processes, trackers, scripts, or logistics information systems. So this concludes my presentation. Thank you for your time, and I look forward to any questions or feedback anyone may have. Appreciate it.
Hello everybody, I am Lieutenant Junior Grade Nurullah Sarikaya from Turkish Navy, and I will be presenting my thesis research as a part of MOOS Summit. So here is today's agenda. My research focuses on evaluating a virtual reality-based diesel engine startup training system called the Mechanical Readiness Virtual Training System, or MRVT. The goal of this work is to explore whether technology can provide an effective, usable, and accessible training environment for novice naval personnel performing shipboard mechanical procedures. For my problem statement, traditional naval simulators have primarily focused on navigation, operations, and ship handling. While these systems are effective for those purposes, VR-based procedural training for mechanical and engineering operations remains relatively limited. At the same time, real shipboard mechanical training can be expensive, resource-intensive, and potentially hazardous, especially when conducted aboard operational vessels. Training opportunities may also depend heavily on ship schedules and operational availability, which limits opportunities for repeated hands-on practice. The images shown here represents both operational engineering environment and VR-based training approach explored in this research. This study evaluates whether immersive VR technology can provide a safe, accessible, and repeatable training environment for novice personnel performing diesel engine startup procedures. The US Navy has continued expanding simulator-based training to improve fleet readiness and operational proficiency. Major facilities such as Mariners Skill Training Center in San Diego and Norfolk demonstrate the Navy's long-term investment in simulation technologies. More recently, the Navy has also explored virtual reality applications for procedural and shipboard training. These VR systems allow sailors to repeatedly practice procedures in immersive simulated environments without depending on operational ship availability. The image shown here illustrates example of Navy-related VR training environments and immersive procedural simulation systems. These developments highlight the growing role of VR technologies within modern naval training and support the relevance of this research in mechanical readiness and engineering procedural training. For this research, we developed the Mechanical Readiness Virtual Training System, or MRVT, using Unity and MetaQuest 3 platform. The goal was to create an immersive VR environment focused on procedural mechanical training. The MRVT simulates a generic shipboard diesel engine space designed for diesel engine startup familiarization and procedural practice. The virtual environment has adapted and expanded from previous year MOOS research and further developed for this study in collaboration with the Future Tech Research Group at NPS. The simulation included interactive valves, gauges, electrical panels, and checklists designed to replicate the sequence of a shipboard diesel engine startup procedure. The study was conducted following approval from NPS Institutional Review Board to ensure proper human subject research procedures and participants' protection throughout the experiment. Participants completed a VR familiarization session to become comfortable with the controls and environment before performing the diesel engine startup procedure within the simulation. During the experiment, we collect both objective and subjective performance data, including interaction logs, task completion time, usability scores, cognitive workload measurements, and participant feedbacks. The System Usability Scale is a widely used usability assessment tool consisting of 10 standard questions. SAS scores range from 0 to 100, and scores above 68 are generally considered acceptable usability. NASA TLX measures perceived cognitive workload across dimensions such as mental demand, effort, frustration, and temporal demand. Lower scores indicate that user experienced relatively manageable cognitive workload levels during the simulation. The simulator sickness questionnaire was used to monitor possible VR-related discomfort systems such as nausea, acclimator strain, and disorientation before the VR exposure. To better demonstrate the MRVT system, I would like to show you a short-in simulation recording from virtual environment. This video demonstrates several parts of the diesel engine startup procedure, including movement within the engine room, interaction with the system components, gauge verification, and procedural text execution inside the MRVT. Results of our research. A total of 30 participants completed the study. Most participations had little prior experience with VR systems, and none had previous experience performing a diesel engine startup procedure on board the ship. The overall usability results were positive. The average system usability score was 80.5, which falls within the good usability range and exceeds the common benchmark score of 68. Participants also reported relatively low cognitive workload levels, with an average NASA TLX score of 15.93. This suggests that users were generally able to complete the procedure without excessive mental or physical demand. The custom training suitability questionnaire produced an average score of 4.48 out of 5, indicating that participants viewed the system as useful for novice familiarization and procedural training. In terms of task performance, 90% of the participants successfully completed the diesel engine startup procedure. Successful participants completed the scenario in an average of 7.5 minutes with an average error count of approximately 3 errors. Overall, participants described the MRVT system as useful, engaging, and effective for novice familiarization training, while also providing constructive feedback for future improvements. For the future work, while the current MRVT system focuses specifically on diesel engine startup procedure, there are several opportunities for the future development and expansion. One important direction is expanding the simulation to include additional engineering and operational procedures, allowing the system to support more comprehensive mechanical readiness training. Another major improvement will be integrating emergency and casualty scenarios into the environment. Examples include system malfunctions, pressure fails, overheating events, and other abnormal operation conditions. These scenarios could better prepare trainee for real-world shipboard situation and decision-making under stress. Future versions of the MRVT could also improve environmental realism and interaction fidelity to create a more immersive training experience. Finally, multiplayer and instructor-guided capabilities could support collaborative and team-based training scenarios, helping align the system more closely with broader naval mechanical readiness training objectives. Thank you very much for listening to my presentation. I would happy to answer any questions.
Good morning. I'm Major Dominik Schwindling, German Armed Forces Army, and his work is my thesis in the MOVES program. The topic is self-organization in heterogeneous drone swarms. My practical question is whether groups of different UAS can coordinate locally under stress and whether humans can still understand what they are doing. The second part is central for military use. Mission success alone is not enough. Adoption of the system also depends on trust, traceability, communications, and also transparent behavior under degraded conditions. After my degree, I'll be going back to the Army Innovation Office in Cologne, Germany. I will walk through the brief in 6 steps: problem statement, some background, my approach, as well as results and ideas for future work. In the end, there will be time for discussions and questions. So the article image in the top is my starting point. Bates and Crick, analyzing US acquisitions, argue that drones are not yet truly swarming, but they could be. The distinction is really important. Putting many UAS in the same battle space creates mass, but not necessarily swarm behavior. Central control especially can become brittle when links degrade, distance grows, or electronic warfare interferes. Heterogeneity adds opportunity for swarm because different drones can sense, relay, suppress, or engage differently, but also makes coordination a lot harder. Many algorithms that I found are not ready for this. So the military problem is not only more drones, it's adaptive, resilient, and transparent coordination, especially without depending on one fragile central controller. Swarming, looking at the nature, is just coordinated local behavior. In this thesis, self-organization is the mechanism used to make that idea executable. The swarm should not wait for one central planner to assign every task. Communication should remain local where possible, and plans really should emerge from interactions among the agents themselves. And I found voting is a major mechanism for this. So scenario figures shows why this is important. The operational value comes from combining different roles, capabilities, and not from treating every role as identical. The science approach fits this because I don't want to only describe a concept. I tried to build an executable artifact, simulation, I tested it, and then I evaluated the behavior that emerges from this. The experiments were conducted in the Swarm Commander Tactics software shown on the right, provided by the MOVE's Future Tech team. The self-organization architecture implemented within it has 5 layers: communication, forming teams, subteams, task allocation, sharing beliefs about observations about the world around them, and finally also engagement. I tested these layers across 18 search and destroy scenarios with different stresses such as jamming, partitioning, wrong initial target information, and also some scenarios with mixed stressors. For the current dataset, I used 5 repetitions, giving a total of 19 retained runs. And the logs capture basically everything: success, all the messages and link outcomes of communications, decisions, beliefs at certain time, safety reactions, and also how the swarm decided to engage the problems presented. The main result is that all 90 runs completed the mission objective. So the important part for me was not just completion. This is not only quantitative work, but also how this completion worked under stress. In one scenario, there was active jamming with only 6.9% of messages delivered at all. There was also swarm partitioning, 500 meter wrong initial target estimate, but they still succeeded. So the top right timeline shows some representative cases. Each dot is a logged event, so the figure shows how success was produced, and not just that it was successful. Team formation, task assignment, changes in beliefs, suppress and strike were all needed at different times in the scenario and to different intensity. The last mixed stress case is longer and denser. That is really interesting because the swarm keeps coordinating, but the coordination cost becomes visible with this. So a lower chart shows transparency by self-organization layer. Layer 0 and 2, they're strongest because communication and task outcomes can be observed directly. 1 and 3 are a little bit weaker because teaming and repairing beliefs or changing beliefs require a lot more inference into the data. So to me, my results are encouraging, but they are still early. The next step is, I think, more quantitative experimentation and also beyond 5 replication. I saw some promising initial tests that even with about only 1% of the initial bandwidth, the swarm could solve many scenarios. And I think that points towards a feature called graceful degradation. So with degrading environmental circumstances, still tasks can be somehow fulfilled. And it doesn't just cut off. But I think this needs harder testing before making very strong claims. Future experiments should push the architecture more, I think, with stronger jamming, lower delivery rates, more wrong initial information, denser threads, and also a combination of these. I think one very interesting extension is swarm on swarm. So if both sides of the conflict adapt to swarm technologies, then decision speed, local coordination is really operationally relevant. I expect this is where self-organization might shine even more in the future. Thank you for listening to my talk, and I'll be open for questions now.
Hello, my name is Major Sean Floeter, and this presentation covers my thesis, a framework for parametric data transparency, simulation conceptual models to build trust, and authoritative data alignment, and simulation outcomes. This research looks at how simulation conceptual model documentation can be used to improve understanding of a simulation function. The goal is to make the relationship between model structure, data, and outcomes more visible to stakeholders. Here's my agenda for today. I'm going to talk about the impetus for this research, how simulation conceptual model documentation supports model understanding, my approach to support creating that transparency to different stakeholders, the results for traceability and comparison, potential future work, and I will stay online for further discussion and questions following this presentation. The problem this thesis addresses is simulation transparency. In many cases, users and analysts can see the output of a simulation and may be able to change parameters in the interface of data or database. What they cannot often see is the pathway between those inputs and the resulting behavior. That creates a black box problem. The simulation may produce a result, but the user may not be able to trace how specific parameters, internal logic, or event sequencing contribute to the result. That makes the outcome hard to inspect, defend, or validate. This becomes more important when simulations are compared or federated. Two systems may exchange data through an architecture, like distributed vector simulations or high-level architecture, but it does not mean they represent the same entities, behaviors, assumptions, timing, or outcomes in the same way. The Simulation Interoperability Standards Organization figure to the right helps show why this matters. As we move above technical and data exchange, the assessment requires more human judgment and more evidence. So the problem is not just the connection. The problem is whether stakeholders have enough visibility into the model logic and data relationships to understand what the simulation is actually doing. Simulation conceptual models describe what a simulation represents, including its assumptions, model logic, abstractions, and limitation. The documentation turns that conceptual understanding into an artifact that users, analysts, developers, and integrators can inspect. The background for this work is that simulation conceptual model is the bridge between what we intend to represent, the referent, and what the simulation actually does, the executable model. The issue is, unless properly documented, the leap from reality to code is too large, and sifting through code is time-consuming, costly, and often unreliable. Users may see database values, interface settings, and outputs, but not the conceptual logic that connects them. For this thesis, I focused on making that bridge more explicit for a single simulation function. That means tracing configured data, runtime conditions, governing logic, event sequencing, and state changes or outputs. My approach was to develop and implement a framework. The thesis product is the framework itself, and I implemented it in 4 steps. First, I bounded the problem to one simulation function instead of trying to document an entire simulation. Second, I built artifacts using event graphs and multi-viewpoint conceptual modeling. Third, I used those artifacts to trace the data, logic formulas, and sequencing, and the outcomes that support that function. Finally, I applied the framework to sensing and target acquisition in 2 constructive simulations, Joint Conflict and Training Simulation, JCATS, and mock technologies as VR forces. The intent was to move from an opaque simulation understanding toward a structured artifact that supports traceability and later comparison. Here are the traceability results. The framework uses multi-viewpoint conceptual modeling to first define the intended use and scope of the bounded function. From there, the narrative provides a plain language description of the entities, actions, and receivers involved in the function. That narrative then helps drive the event graph into behavior view. The event graph captures the sequencing, conditions, triggers, and state changes. The behavior view decomposes those events into model actions and decision points. The framework then further decomposes that information into data and formula views. The data view identifies the necessary data, variables, parameters, and sources. The formula view shows how selected variables enter equations, lookup tables, or other logic. Those two views are complementary because the data view tells us what values matter, and the formula view shows us how those values are used. The final result is documented artifact on the right, a structured, traceable, interpretable, and comparable representation of the simulation function. Comparability is not just about matching variable names or setting the same values in both simulations. The framework helps show whether the simulations use similar concepts in the same way. In the case studies, both systems can represent a similar sensing situation. The simulation conceptual model artifact showed that the underlying model logic is different. That matters because two simulations may appear aligned at the input or output level while still producing behavior through different internal assumptions and sequencing. This is where the framework supports interoperability analysis. It helps identify whether the simulations are comparable enough for intended use, or whether differences in model logic could create hidden advantages, disadvantages, or fair fight concerns. Future work moves in four directions. First, the framework needs to be tested against other simulation functions such as movement, engagement, damage, or logistics to see how well it generalizes beyond just sensing. Second, the framework could be used to inspect data pedigree by tracing where values come from, how they are selected, and how they affect model behavior. Third, the artifacts could help isolate which parameters or logic points should be controlled, tuned, or tested before simulations are federated. Finally, future research should examine whether the framework can support verification and validation for intended use, providing clear evidence what the simulation represents and how it produces outcomes. Thank you for this time. I will be happy to discuss the framework and my research in further depth.
Good morning. I'm Colonel Marcio Nakano from the Brazilian Air Force, and today I'm presenting a framework that aims to transition Brazilian Air Force from a reactive maintenance posture to a predictive approach. The agenda follows these sections. Problem statement. Next, in the background section, I will establish the theoretical foundation. In the approach, I will detail the methodology employed. The heart of the presentation is the results. In the discussion, we will interpret these findings. I will conclude with future work and open for questions. Our embedded avionics suite has exceeded 20 years of operational service, transitioned out of their stable useful life period, and have entered the wear-out phase. This technical degradation forces an economic balancing act. On one side, we face a substantial inventory risk. As Blanchard notes, maintaining high stock levels is financially impractical. It results in immobilized capital and exposes the Air Force to technological obsolescence as systems undergo modernization. Conversely, we face an operational risk. A lean inventory posture is currently inadequate to mitigate the rising frequency of failures. The result is immediate simulated downtime, which creates backlogs in pilot training. Our research identifies a current need. We must move away from mass-based logistics and toward an information-based model, ensuring availability without budgetary waste. The Brazilian Air Force operates an integrated maintenance system. Our central depot does not hold independent avionics stock. Instead, we rely on the same supply used by our aircraft. Command Instruction 1 is the regulatory logic we must follow in Brazil. It requires authorization for each single avionics part to be used. This creates an administrative loop that starts the clock only after the failure is detected, leading to the downtime in our flight simulators. We are currently trapped in a reactive break-fix philosophy, where the repair is only performed after failure happens. My research proposes a to-be state, a predictive system where we use information to neutralize the administrative delay by prepositioning parts before the failure happens. Discrete event simulation allows us to model the system as a series of specific events. A failure occurs, a request is sent, a part is shipped. This is crucial for capturing the stochastic variability. in how often parts break and how long it takes to move them across Brazil. We choose Synkit, a Java open source package developed here at NPS by Dr. Buzz that uses event graph methodology. This gives us deep control over the mathematical logic and allow us for a modular architecture. We can build one supply chain component instantiate in different remote depots, reflecting the Brazilian Air Force actual geographic dispersion. The core of our operational integration is the adaptive time-based model framework. The breakthrough here is signal decoupling. In our framework, we use a predictive trigger to start the logistics clock while the component is still functional. By utilizing the component remaining useful life as a lead time buffer, we allow the administrative and transport delays to occur in the background, ensuring the replacement part arrives before the operation part fails. To manage these geographically dispersed simulators, the model centralizes coordination at the central depot. By centralizing the prognostic sensor logic at this depot, we can optimize inventory distribution across all remote sites. In the current as-is reactive posture, the logistics and administrative sign is physically tethered to the component's failure. By decoupling these, we separate the administrative authorization from the physical arrival of the hardware. The operational implementation of this decoupling is the predictive trigger. We treat the simulation as a prognostic sensor that monitors the remaining useful life of every installed component. When a part crosses a calculated wear threshold, a replacement request is initiated. The objective here is latency absorption. We aim to hide the stochastic delay of the transportation and bureaucracy within the part's final hours of life. We utilize an object-oriented approach with every avionic component instantiated as an entity. Then we assign each part a weighable-based life expectancy to models a wear-out profile, where the probability of failure increases as the component ages. The simulation logic is governed by the event graph paradigm. This allows us to model the moment a failure is scheduled, a request is triggered, or a part arrives at a remote base. By managing these at discrete point in time, we can measure the latency between a maintenance signal and the logistic response, which is the core bottleneck we are investigating. The event graph model has three core components that I will detail in the next slides. The initialization phase establishes the fundamental parameters and stochastic conditions of our modeling environment. We parameterize the system with reliability data, specifically employing weighable distribution with shape parameters that reflect wear-out characteristics. Furthermore, we account for geographical and operational heterogeneity by assigning distinct utilization rate at to different simulator sites. During the operation phase, the simulation manages the life cycle of each asset through a discrete event simulation architecture. Here, we track each line replaceable unit by its unique serial number. This allows us to implement a stock clock logic, ensuring that component degradation is only recorded during active utilization, thereby accurately reflecting the aging process of actual aircraft avionics hardware. The maintenance module serves as the analytical core of this research, contrasting traditional reactive posture with the proposed ATBM framework. The system is programmed to identify a critical window, triggering a proactive demand signal. To reflect real-world Brazilian Air Force constraints, we model bureaucratic vetoes. Every technical request has 40% probability of being rejected. This identifies the breaking point where administrative friction overrides our technical advantage. Success is measured by two key metrics. First, achieving a 20% improvement in the operational availability to reach the 90% readiness floor, and second, a 35% reduction in stockouts, proving that predictive data can effectively replace for physical stock. The results: A29 simulator improved from a reactive mean of 68.4% to a predictive mean of 92.4%. The T27 mic increased its availability from 72.2% to 90.3%. This relative gain of 20% confirms that the predictive trigger effectively internalizes logistical weight states. By initiating procurement while the component is still functional, the model transforms potential simulator downtime events into planned maintenance actions. 829, under the corrective strategy, the simulator suffered 88 unplanned failure events. By transitioning to the predictive strategy, this number plummeted to about 38, a reduction of 55.13%. T27 Mike had a reduction from about 35 events in the status quo to about 20 in the 8BM scenario, representing a 43.27 decrease in unplanned downtime events. This reduction is the most significant confirmation of the information versus mass trade-off. By triggering logistic demand based on the component remaining useful life, the system absorbed the 40% administrative vet friction while the simulator is still operational. For the future work, first we must expand this logic to our C105 Amazon simulator. Future work should evaluate if the predictive logic can maintain the availability floor for the simulator. Second, a logical progression is to transition this ground-based study to our actual operation fleet. Third, by using machine learning to analyze historical procurement data from central depot, we can forecast periods of high vet probability, such as the period of high utilization of the hero aircrafts. This allows the system to dynamically adjust its lead time buffer to outrun expect peaks in bureaucracy latency. This concludes my presentation, and now I open to the questions.
Hello, Move Summit. My name is Captain Finnegan. I am I'm in the United States Marine Corps. My future billet's going to be the TCOM Integration Center in Quantico, Virginia. And I'm here to present the computational fluid dynamic framework for modeling and AI estimation of ship wakes. Just to give some background, I was with LER for about 8 months for my platoon commander time, and then I got picked up to be the Maritime Reconnaissance Platoon Commander under 1st Recon, and we specialized in VBSS and over-the-horizon targeting, and so that was a factor for choosing my thesis topic. There's my email, there's my phone number, and my advisor, Professor Brown. Big shout out to him for helping me and being patient with me. Here's the agenda. I expect 20 slides today, and let's go on and get into it. So my problem statement: modern drones and aircraft too easily spot the bubbly wakes produced in small boat operations. Here on my right-hand side is a picture from some training with my Marines. Nighttime, the boat itself never could be spotted. If it was stationary, very hard to find, but we had to balance time and speed while in the area of operations in order to reduce the risk of being spotted. So here you are. You can see from a UAS that it's not the boat that's being spotted, but that bright optical signature, those bubbles refracting the light, that is actually what causes the visibility. More historical example, Battle Midway, where the altitudes the pilots are flying at, it was very likely the long tail of the Japanese warships going at flank speed. That is likely what led to the compromise, as opposed to them being able to see the actual ship itself. And that one vessel being spotted that led the Allies to the actual Japanese fleet itself, that was a huge momentum change for the Allies in World War II. So how does this actually happen? What causes the bubbles? There's a few reasons. Number one, going around the horn, is that we call it hole slapping, where as the boat lifts up after a wave, it slaps the water, and with it, the air gets entrained, and then it just glides along the back. There's also air injection or prop cavitation, depending on the boat, and the wake itself can generate some bubbles, some micro bubbles. In a boat wake, we need to be able to track the bubble size distribution, since the density and diameter of bubbles lead to different optical signatures. To do this, we use the solder mean diameter on the middle of the page. That's at D32. It is a ratio of the theoretical sphere that has the exact volume to surface area ratio as the entire collection of the particles. So it's just able to collapse down an entire area into one single bubble to describe the population itself. And then we're also using a radiance surrogate derived from my scattering theory. Not mine, but my scattering theory. It's acting as a summation of the inverse diameter of the individual particles. The theory states that bubbles with a smaller diameter but the same amount of volume as a larger bubble, those particles itself will actually refract light stronger than a single bubble will of the same amount of volume. Depicted on that bottom right is that bubble size distribution of, hey, we need to be able to understand the makeup, the properties of the wake. And then depicted further on the right is taking a look at small bubbles. If a laser or light hits one bubble and it's able to hit a lot going on inside of that, it's kind of a much brighter, much different optical signature than just a single lone one. Together, these can help us derive and quantify the optical signature in a wake without having to dive into the true radiance. So the research questions is, how do we abstract the physical interaction and computational cost of resolving chemical, electromagnetic, and novel technologies and compressible physics? How can mitigation devices be used to alter the visible signature of ship wakes? And lastly, can we leverage AI to produce wakes and calculate properties of the original vessel from its observed wake? Here's a top-down conceptual model of my framework that we developed for our thesis. It's a lot to take in, but just one at a time. So the top of the slide, it's depicting a parallel run between the vendor's brought simulation and its framework simulation. It is just going to be a simple base case. You put in a hole and you run it through without any mitigation devices turned on. You just want to make sure that all of our input variables line up, such as the hole shape, what models are you using to calculate energy dissipation, for example. You just want to make sure that's all lined up. And then you turn on the mitigation device. So the vendor will present their own mitigated wake. They're going to tell us what was input to generate that wake. And so here depicted the input variables E through J. It doesn't matter what those are necessarily. This framework will distill those E through J variables into just a simple KLM. And for example, it could be a R input variable. The vendor could say our input variable, the electromagnetic input, it forces bubbles to merge 10 times faster. And so instead of having to code and verify all that complex physics of how an electromagnetic input can merge bubbles 10 times faster, we just simply add a modifier to the merge rate and say, okay, cool, we're just simply merging bubbles 10 times faster in its sphere of influence that the vendor has told us. So then we run through multiple iterations of that, and we have, instead of 10 times faster, we maybe have it 15 times faster, 5 times faster. It gives us some parameter play space, and it gets us, as you can see, instead of having a steady state output of 1, 2, 3, 4, we have maybe 0.6 to 1.5, 1.6 to 2.5. This is all just conceptual, just to show that, hey, an AI can then interpolate, and we can give that vendor some grace in what that final wake looks like. So it doesn't have to match up exactly with, they say 10 times. This AI can interpolate and say, oh, it's actually close to 13 times. Yes, it makes sense. Your final product, we are able to validate your final wake with our parameters. So getting into the actual approach. So for this computational fluid dynamics approach, for the ground truth generation, we're using OpenFOAM version 10 with the multi-phase Euler foam solver. What this allows us to do is have a continuous phase, the water, and disperse phase, the bubble flow. We're able to separate those two, and we're able to put the bubbles in separate bins. Instead of just having one size fits all, instead we're able to have a mass flow between bubble bins in different sizes in order for us to capture that, my scattering theory, which is the smaller diameter, higher radiance value. So depicted on the bottom left, there's that mitigation device that the vendor could come up and present us with and say, hey, my device merges bubble 10 times faster. Here's the size that it can actually affect. And hey, you know, as it gets farther away, maybe it only merges bubbles 5 times faster. This framework can capture all of that, and it's able to produce a validated wake of what it may look like. And so there's that abstracted mitigation device regime where it's different merge, different breakup, different dissolution rates, and then downstream produces that radiant wake. So just to explain the mitigation device, OpenFOAM version 10, we are using the Eulerian-Eulerian merge and breakup models. And then we had to custom implement the Epstein-Placet dissolution model. It just wasn't available in the solver being used, but it's another validated model that has been used in different CFD cases. And so just to very put it simply, the merge The Eulerian-Eulerian merge model, it's a probability based depending on how much air is in that cell. The breakup, it is a energy dependent, and so it's a scalar multiplier of our device saying actually you need 80% of the energy required to break a bubble. And then the dissolution, it is how a bubble dissolves into the fluid around it, and multiply for that, it just multiplies the mass transfer rate from the bubble bins to the lower bubble bin until eventually just dissolves. So here's some results. Just to cover what we can actually analyze, we can track the solder mean diameter, we can track the radiance, the total air entrained, bubble size distribution, the interbin transfer, the number of physical events that actually occur. Here I just wanted to show the integral of the bubble fraction over the port, starboard, and depth of the distance of the wake. Right at the propeller, there's a spike of air as expected. That is what we're modeling. We're modeling some propeller cavitation. And then as the wake evolves, the air is decreasing, either due to bubbles merging, rising faster, degassing, or just that dissolution down the line. And then we're just able to measure that. And then we have a 20% total air. It's going to represent as a relative zero, just because there's always going to be a little bit noise in these simulations. So we take the last 20% of the data, and we say that actually that is just going to be the relative zero for no more air existing. So that's what that gray dotted line is. The bottom graph is showing the backscattering coefficient. Essentially, that we're using that as a radiance surrogate. And it just takes into account the properties of the bubble size distribution. So what's the number of the small bubbles? What's the number of the big ones? How does that take into account? We, of course, utilize the inverse diameter, summation of it, and we use that as a surrogate. And then we can just see the evolution of the radiance as it moves along down in the x-axis, which is the downstream wake. As the bubbles merge, rise faster, and degas, the intensity, as expected, decreases. Dissolution is also in effect. This case right now, it's actually the AI held out case. So the breakup, the merge, and the dissolution are all set to 80 times intensity. We can just see what the resulting wake looks like. Some results of the actual physics and of us running it. One result is that we're able to derive the power and piecewise mathematical models that accurately describe a bubbly wake's behavior. The intent is to provide a lightweight, solvable surrogate mathematical model that can simplify the prediction of the optical signature. This is just to get future simulations away from kind of just artistically depicting the bubbly wake and instead making it an actual probability detection and just giving it real properties. Because from what we have seen, it's always been, well, it's too complicated. We're just going to make it an artistic choice as opposed to a real physical aspect of the simulation. Other mathematical models that we derived include where the wake changes from a high turbulence to far momentum driven. We're able to describe the degassing length, wake widths. This can help with future modeling bubbly wakes by attaching a decay equation in order to generate the wakes. Presented here is a simple power law decay rate of the actual radiance. So left-hand side is every case that we ran. And then the bottom, the x-axis, that is the decay exponent to describe how the actual radiance, how that optical signature decays over time. And then the right-hand side, it's actually the wake width. So that exponent is a spreading exponent to describe the second moment of how wide the optical wake can get. Moving on to our AI ML pipeline, we created 4 total models. There's a YZ integrated per bin volume network. What this is it predicts each bubble bin's entire population and volume. It's a full 3D model replication of the wake. Second model was a surface reflectance model. We wanted to make it more targeted, so it's only going to be about surface deep. It's only about a meter deep, and it's supposed to specifically just replicate a optical signature from a top down, as if a sensor was, as if a UAS was seeing it from overhead. The third one is a bubble size distribution teacher model. It is a 0-dimensional one. All that teacher model understands is what is the makeup of the 12 bubble bins. That is just to constrain the models 1 and 2, just to create realistic bubble size distributions. The fourth one is a simple air injection surrogate model. Again, to this more detail, but it utilizes it just for a proof of concept due to lack of high power computing time. So speaking of the limited high power computing time, we were only able to about have 7 usable cases. There are some cases that were set to very extreme rates just to prove that the framework was working. And so with that, we have about 7 cases. One of them was a validation case. Another one was a holdout case. So it is a limited AI that's able to train with limited data sets. Future work, we would like to have more anchor points, just so the AI can better understand how those different rates contribute to the final wake optical signature. But I said before, the holdout case that we're going to be examining is going to be 80-80-80. So fragmentation coalescence dissolution rate is set to 80. So here are the results for the 3D profile generation. The AI does seem to struggle with the smallest bin. It is likely because the smallest bin, the inverse diameter, it has a 1 over diameter rate. And so a small error does add some unintended consequences. Just because as it's trying to learn, oh, hey, this bubble really affects radiance. I need to make sure I'm really tracking it. It does lead to errors down the line. But as the bubble bins increase, AI does seem to understand the distribution better. Right-hand side is using that radiant proxy, or the radiant surrogate, to describe the optical signature of the wake. Despite not grasping the smallest bubble bins, it doesn't make up the largest distribution. So it's actually fairly decent at a 95% R-squared value. For the 2D surface model, again, the held out was the 80-80-80 as well. Again, fairly confident with this AI to be able to create a 2D surface model. It is a .pth.path output. It's capable of integration with Open Neural Network Exchange. So it's able to run in game engines such as Unity, Unreal. So it's just able to quickly generate those wakes, as opposed to making a simple artistic sacrifice of saying, hey, it's just white water. And instead, we can have an AI that can say, oh, you want these parameters? Here's the optical signature. It is also capable of a VTI imaging or sticker mesh output. If we just want to make it even more simpler, instead of having to run an AI to generate these wakes, instead just apply a sticker to Unreal, to Unity, and we're able to just get better training out of those simulators. On the right-hand side, that is just a reconstruction of the CFD and the AI radiance. And the far right-hand side, it's the difference. And again, it's just showing that it's getting the shape well. It's maybe missing some of the peak brightness that we would like to see, but it's just mostly because the training set is missing those anchor points as described earlier, such as like pure coalescence, pure dissolution, pure fragmentation. Here is the bubble size distribution teacher. Again, it's zero-dimensional, but it's very good at understanding the final distribution of what the wake should contain in terms of bubble sizes. And again, this was used essentially just to make sure that our 3D and 2D models were generating data correctly and not having crazy results and having extremely large 10 micrometer size bubbles. This is probably going to be the most operationally relevant portion of this thesis. On the left-hand side, here's a photo found on Instagram, open source. And the motivation is that, hey, if we have an overhead image of a known vessel's hull, its speed and its location, just so we can get the water properties. And if we have an AI that was trained on that hull and can generate wakes of that hull, are we then able to inverse the inputs that created that wake? Well, that's what all this is saying. On the left-hand side, this is that very simple air injection model. So it's without a hull. It's just simple air injection with the mitigation device turned on. It was trained on a very large training space because it was able to run on, once you add a hull to OpenFOAM, it's a lot more difficult to run cases. And so we were able to run this just on we had a lot more compute time on its node. And so the observed target, and again, this is a held out data for the AI. So it's never seen a 50-50-0 before, but it's seen data that was above and below it. And so the ground truth, the CFD data was collapsed into a 2D image. And then there was an AI and it ran, it was optimization run through. And it was using that AI and it was rapidly generating the wake. And it was attempting to match the input parameters as close as possible to get the ground truth data on the left. Bottom is what the actual AI was able to recover. And so its best final guess was it was a 47.4 breakup rate as opposed to Secret 50. And it guessed a 43.1 coalescence rate when the Secret was 50. And it guessed 0% for the dissolution. And so on average, about 6.5% error. And so that to us felt like if the information is in the wake, optical signatures carrying a lot of information and moving forward future research should focus on, hey, how can we pull that optical signature into real data? And I'll get into more what that means later. So here's just a result summary. The 2D and 3D AI models and mathematical power law piecewise models to generate physically accurate wakes. We're able to abstract the effects of future complex novel technologies without having to code the physics of each technology. So it's modular, it can take in whatever a vendor may come up with, and then able to invert the input parameters that generated the wake, proving future work can feed the intel cycle by converting 2D images into actionable intelligence. For example, if a fishing vessel shows up light and it leaves the port heavy, from the AI is able to deduce you're carrying about 8,000 pounds of equipment, likely target a VBSS hit. Future work, as I said before, just wanted to show that it's not a data density problem, it is a anchor point problem. We need more pure cases in order to improve the AI results. At this moment, I will go ahead and pause, and I'll be present for any questions. Thank you.
Hello, I'm Lieutenant Mary Rassicott. I want to talk to you today about a problem that lies in the intersection of cyber and constructed simulation. My topic for today is automating cyber entity generation for semi-automated forces, a methodology for integrating logical network data and kinetic simulations. How do we get cyber into kinetic simulations? In most exercises today, cyber looks like this. Someone writes a script that says at t plus 30 minutes, blue force loses comms. And that's the entire cyber effect. It gets injected into the scenario, things continue, training happens, and for some purposes, that's fine. The problem is there's no network behind that script. The causal chain exists only in the scenario designer's head, and that means you can't analyze it, you can't reuse it, and you definitely can't verify that it was implemented correctly. There is no way to go beyond comms loss to cyber attacks on power grids, gate controls, or radars. The M&S community invests heavily in standards for exactly this reason: interoperability, composability, and traceability. And CISO recognized the cyber gap. In 2024, they published the Cyber Data Exchange Model, a standard that defines exactly the entity types we need. But a standard only helps if someone generates those entities. The trouble is, how do you take a network model with dozens of radios, workstations, SCADA systems, routers, and more, and quickly decide what gets entities, what characteristics they need preserved, and how they interconnect? Then you have to actually make all of those entities in your simulation. No method exists yet. This research builds it. I want to be clear about scope. I am not modeling cyber attacks. This is a foundational step that has to come before any of that. A rigorous, repeatable process for generating the cyber entities that would populate constructive simulations. 3 concepts underpin this work. The CyberDem, it's the common language for cyber entities simulation. A device has a type, an operating system, services it runs, stable identifiers, networks have links. Everything is typed and relational in a way that people can agree upon. It was designed for interoperability across simulation systems, so think of it as a data contract letting cyber entities move between the federates. GIS, Geographic Information Systems. Most of you are likely thinking of maps and terrain. I'm using it as a schema-enforcing computational workspace, a geodatabase that can hold an inspectable, intermediate state that a human can look at and reason about. And DSEEP, providing the life cycle framework from which I'm operating. The key principle that I carry forward is iterative verification, embedded at every transformation boundary, not just as a terminal check at the end. This means errors get caught early and can be traced to their source. The methodology I developed has 5 layers, and the key design principle is that each one produces that inspectable artifact at its boundary. You don't have to trust the process end to end, you can look at what each stage produced and confirm it's correct. Layer 1 is data abstraction. The source data in my proof of concept is Ansible infrastructure as code, YAML files, that declare what devices exist, what's installed on them, and what networks they belong to. The abstraction layer parses all of that, resolves variable inheritance across multiple files, and produces one normalized record per device. Everything is consolidated, but it is not standardized. Layer 2 is semantic mapping. This is where we cross from network administrator terminology into CyberDem terminology. Each device gets a device type from the standards enumeration. Its operating system gets an OS type, service types, etc. Every entity gets a stable deterministic cyber object ID, and the keyword there is deterministic. Given the same input, you always get the same identifier, and that is essential for traceability. Layer 3 is geospatial integration. The mapped entities go into a geodatabase. That geodatabase does real work. It rejects domain invalid enumeration values at ingest. It enforces referential integrity between entities and gives analysts a human-readable intermediate state. I also implemented what I call a geohint mechanism, a principled way for a human analyst to associate a cyber entity with a physical building or entity without baking coordinates into the CyberDem itself, which, by design, has no geospatial field. Layer 4 is transformation and export. The verified entity graph gets serialized into JSON and XML, portable, machine-ingestible artifacts. Identifiers and relationships are preserved. No inference, no reconstruction. It is CyberDem compliant entities ready to ingest into whatever constructive sim you're implementing. Layer 5 is verification, and this is not a separate final step. It's woven through every layer boundary. Entity counts can be confirmed, identifier stability checked, cryptographic hashes of inputs recorded in execution manifests, so that you can later prove that the same inputs produce the same outputs no matter how many times you run it. So let me show you what the raw inputs look like. Ansible organizes network configuration across multiple files, an inventory listing all of your hosts, group variables with shared enclave settings, and host variables with per device specifics. To understand any single device, you need to consult at minimum 3 different files. In the middle column, you'll see the inventory. HQ DC1 is listed under the HQ group with its IP address. On the right is HQ DC1's host file, domain controller, Windows server, critical service, listening on 4 ports. But the subnet and security zone are in the group's variable file, a completely separate lookup. That's the consolidation problem that Layer 1 solves. 1 device, 3 lookups, and 1 normalized output. At each transformation boundary, we're going to track that same domain controller. So on the left, you have the Layer 1 output, a flat, normalized JSON record with hostname, IP, role, OS, services, etc. Everything is in one place, so you don't need to conduct multiple file lookups. In the middle, after Layer 2, is semantic mapping. The record now speaks CyberDem in a sense. The device has a cyber object ID, a device type, an OS type, service types, etc. The language is changed from network administration language to simulation interoperability terms. And on the right, the Layer 5 clean export. The entity is now fully relational. Interface structures linked to network entities by ID. Relationships are explicitly serialized. That is what a downstream simulation can consume to understand not just each individual entity, but how they connect. So the same device, 3 representations, each more structured than the last, and every transition is traceable from source to output. So here's what the test network, for my case, looked like inside the GIS workspace. Top right, you can see the network administrator style network graph. Now compare that to the methods Layer 4 GIS representation, bottom left and center. 2 views of the same 15-device network. On the left, a geographic map view. 15 devices placed across 3 buildings on a notional installation. The geohint mechanism allowed an analyst, myself, to associate each cyber entity with a physical location based on its source data without touching the CyberDem schema, which has no concept of physical geography by design. On the right is the link chart, the logical network topology. Same entities now showing their relationships. And this view is reconfigurable. You can view service distribution across devices, closeness and centrality, choke point analysis across the network. At scale, it allows an analyst to understand a 200-node network before it ever touches a simulation. It's not just a map here. GIS is serving as a schema-enforcing, spatially aware computational environment, and it's giving me an opportunity to analyze, assess, and explore the data before exporting it into a final entity graph. At the far end of the pipeline's proof of concept sits CyberBoss, a simulation management environment that maintains simulated cyber device state and projects cyberspace effects into constructive platforms like OneSAF. It's the bridge between a structured cyber entity graph and actual constructive simulation execution. I built a conversion layer that takes the clean JSON export of my methodology and translates it into the YAML format that CyberBoss is capable of ingesting. All 15 devices loaded with some reconfiguration due to differences in data standard. The pipeline reaches all the way from those Ansible source files into a simulation environment that can federate to constructive simulations. Future work falls into 4 areas: GIS as a live federate, automation and scaling, platform development, and multi-domain extension. The key finding, though, is that current SAF platforms cannot receive cyber entities because they lack the necessary entity formatting and communication models to represent cyber. This is the #1 area for future work. To close, this research makes 4 primary contributions. First, a methodology for transforming network data into CyberDem compliant simulation entities. It is repeatable, deterministic, and traceable. Second, a demonstration that GIS can serve as a computational workspace, not just a map viewer. Third, a structural identification of the schema gaps that block accurate cyber representation. And fourth, specification of what OneSAF in particular needs before it can host cyber entities at all in a native format. The 4th contribution reflects the broader findings. Constructive simulation platforms are not ready for cyber. The incompatibilities are generally structural. Network topology has no native representation, or geolocation requirements exist that are incompatible with a CyberDem. The methodology enables you to take heterogeneous network information and in a semi-automated fashion produce CyberDem compliant entities for ingest. Step 1 of cyber in constructive simulations complete. Thank you. I look forward to discussing further in the breakout groups.
Good morning, everyone. My name is Captain Tai, United States Army. My thesis is titled Enhancing Logistics Battle Command, LBC, for Reinforcement Learning, Enable Decision Support in Contested Logistics Environments. This research examines whether reinforcement learning could be integrated into an existing logistics simulation to support sustainment decision-making under contested conditions. I want to be clear about the scope. This thesis does not argue that AI should replace planners or commanders. Instead, it treats reinforcement learning as a bounded decision support layer within a controlled modeling and simulation environment. The goal was to preserve LBC as the core simulation, add a limited learning layer for provider selection, and evaluate whether that layer could improve decision behavior while remaining explainable and controlled. I will walk through the brief in 6 parts: the problem statement, background, approach, results, future work, and discussion. The main point is how adaptive decision support can be integrated, tested, and governed inside a military simulation environment. The problem I am focused on is how to test logistics decisions when the environment is changing and under pressure. Legacy logistics simulations are useful for planning, but contested logistics adds another layer. It is not just about moving supplies from one point to another. It is about how the system makes decisions when providers are stressed, routes are at risk, timing matters, and resources are limited. LBC gave me a strong simulation structure to work from, but it does not learn from repeated contested runs. Reinforcement learning, however, can learn from repeated runs, but for military use, it has to be tested in a way that is controlled and repeatable. That is the gap my thesis addresses. This research is grounded in contested logistics. Adversaries can pressure sustainment nodes, observe patterns, disrupt routes, and affect resupply timing. For simulation environment, I use LBC. LBC provided the logistics simulations core by representing sustainment nodes, demand, supply flow, and provider relationships. For an M&S perspective, the gap is not the logistics structure. LBC provides that. The gap is how to evaluate a learning-based decision layer under controlled contested conditions. This gap shaped the approach. I used a fixed logistics network, scripted interdiction, and repeated simulation episodes to create a controlled testbed. My approach was to keep LBC as a simulation core and add reinforcement learning as a limited provider selection layer. The agent's role was intentionally narrow. It did not control the entire logistics system. It did not change the routes, quantities, convoy timing, demand generation, or the network structure. When a resupply request occurred, the agent selected one of the 3 available providers. The model observed a 75-dimensional logistics state that came from 15 logistics features stacked across 5 time steps. The action space was a discrete 3, so the agent had 3 provider choices at each decision point. The reward function was designed to balance several logistics priorities, including field performance, provider health, risk, timeliness, and network sustainability. After the training, the 250,000 step DQN checkpoint was frozen and used as the final model for evaluation. This allowed the evaluation to focus on how the fixed policy performed rather than on continued learning during the tests. The evaluation was built to compare fixed decision policies under the same conditions. Once the 250,000 step DQN checkpoint was selected, it was frozen. After that point, there were no reward edits, no architectural changes, and no additional learning during evaluations. I compared the 4 policies: no agent, random, heuristic, and the train RL policy. Each policy was evaluated against the same 30 fixed seed conditions so that the comparison stayed consistent across agents. The most important part of the evaluation was the survivability first structured. A policy had to avoid stockouts before reward, efficiency, or algorithmic performance mattered. That kept the evaluation aligned with military logistics priorities. In this framing, mission survival comes first, decision quality comes second, and algorithm performance comes after that. The main result is that all 4 policies preserved survivability. In this evaluation, that means every policy completed the primary runs with 0 stockouts. Because survivability was equal across the agents, the next comparison was decision quality, efficiency, and stability. Within that survivable operating space, the train RL policy achieved the highest mean cumulative reward at 8,423. The heuristic policy was next at 6,422, followed by no agent and random. The RL policy also produced 0 reward variance across the fixed seed evaluation, which shows stable behavior under this specific test setup. The important point is that RL did not create survivability by itself. All policies survived. The value of RL was that it made stronger and more consistent provider selection decisions after survivability was already preserved. A major part of this thesis was governance. A higher score by itself was not enough. I also needed to understand what the RL policy was doing and where a control mechanism might be needed. After the evaluation, I used explainability outputs and doctrinal alignment analysis to better understand the RL policy's behavior. The RL policy achieved 67.1% overall doctrinal alignment, with most of the divergence concentrated in supplier selection. That number needs some context. Lower doctrinal alignment does not automatically mean the RL policy failed. The alignment rules were a simplified post hoc framework for interpreting decisions after evaluation. The RL policy was not trained to maximize those rules directly. In some cases, it made trade-offs that departed from the simplified rule set while still improving reward and stability. That is why I treated doctrinal divergence as something to analyze rather than an automatic failure. I also tested a hybrid guardrail concept. The guardrail only overrode 12 decisions out of 3,119, or 0.38%. That means the guardrail acted as a narrow safety layer. It did not replace the RL policy. It preserved RL decision authority in 99.62% of cases while still providing a control mechanism for rare critical conditions. The main contribution of this thesis is the modeling and simulation framework. First, reinforcement learning was integrated into LBC without replacing the simulation core. Second, scripted interdiction created a control contested testbed for comparing policies. Third, survivability was separated from efficiency, so reward did not become a substitute for mission success. Fourth, governance was built into the framework through frozen models, deterministic evaluation, explainability, doctrinal alignment, and guardrails. The bottom line is that this is not a claim that one RL algorithm solves contested logistics. It is a disciplined M&S framework for testing adaptive decision support. For future work, the main goal is to preserve the governance structure while increasing operational realism. The first step is adaptive adversaries, moving from scripted interdictions to red policies that reacts to blue behavior. The second is human planner validation, comparing model decisions against professional sustainment planners and COA reviews. The third is network variation, testing different topologies, echelons, routes, and joint sustainment structures. The fourth is expanding the decision space beyond provider selection to include quantities, routing, timing, and multi-commodity coordination. Finally, the guardrail threshold should be stress tested across different criticality settings. The main takeaway is that reinforcement learning can improve decision efficiency after survivability is preserved, but only when the model is controlled properly. For analysts, this provides a way to stress test sustainment decisions under controlled, contested pressure. For simulation designers, it shows how adaptive behavior can be integrated into a legacy model without replacing the original simulation. For AI integration, it provides an example of controllable autonomy where the model makes decisions in most cases, but a guardrail remains available for rare critical conditions. This concludes my thesis brief. Thank you for your time and listening to my thesis and its research. I'll now welcome any questions. Thank you.
Hi everyone, I'm Itai, and I'm going to present my thesis, which is on unseen dawn detection using synthetic data. All right, so what is synthetic data? Synthetic data means an images that we got from a simulation and not real world. So the agenda is going to be problem statement, background, approach, results, future work, and then discussion, if you have any questions. So the problem statement. So what is the problem that we're gonna try to resolve or trying to do our research about it? So it's basically two different things. So the first one, it's two difficulties. The first one is to detect the drone, and the second one is to determine whether it's a drone that the algorithm knows or it doesn't know. So I will go and start by explain what we're gonna referring as in distribution and what we are going to refer as auto distribution or OOD. So in distribution means drones that the algorithm knows and being trained on. And what auto distribution means, in our case, it's drones that an algorithm never saw. So basically, auto distribution means anything that the algorithm never saw. It could be any object, but we are going to examine near auto distribution, which means that you're going to use drones to train and drones to detect, but they're each going to have slightly different features. So what makes it difficult? First off, it's long-range drones occupied very few pixels. So the main picture, this is an image that as is going to train the algorithm on. So for the human eye, you can see the drone pretty clearly, not very clearly, but you can actually see it in the picture. But when we zoom in the right, we have two different resolutions that I'm going to discuss it later on. The upper image, this is a higher resolution. And this is 1024 pixels on 1024 pixels. Of course, it's zoom in for us to see. In the bottom image, we can see an image that is 640 pixels on 640 pixels. So it's almost a half of the upper image. And you can see that in the upper image, we can see slightly more features and more pixels, but on the image below, it's really hard to see and the drone is really blurry. So another thing about this problem is that real-labeled drone imagery is very limited, but I'm going to discuss this later on. So these are the drones that we used in this experiment. So the left one, they are slightly bigger. These are our in-distribution drones. You can see that all of them are pretty similar to one another. They're each gonna have the same color, but slightly different features. From this angle, we are pretty sure that they are different from one another. The right one is auto-distribution, so you can see it's very similar to the others, but it's also a different one with different features. On the far right, you can see this is a real image that you're gonna test the algorithm on. This is in higher resolution, so we can actually see maybe the algorithm could actually detect that this is a different drone. So why use a simulation for this? We'll start by why now. So realistic simulation is making it all possible. So right now we have simulation that could really help us and could generate really good images that we can use to train the algorithm on. And for us, we used NVIDIA Omniverse, and we used it to control the distance of the drone from the camera. We can actually determine what the focal length is going to be and what is the position of the drone. And we used the distance. We used 1 kilometer to 1.2 kilometer, and we used focal lengths that it's pretty reasonable to regular cameras. And yes, the main shift study here is the unseen drone identity. So we want to evaluate methods of auto distribution that can give us a result whether drone is in distribution or auto distribution. So we used an algorithm called YOLO, which is pretty common algorithm in computer vision. We used YOLO version 8 to be specific, and we started by developing the pipeline. So the pipelines goes as we generate the images from the NVIDIA Omniverse, and then we adjust the labels to be as the labels supposed to be for our specific algorithm, which is YOLO version 8. And what labels means is basically means what object is in the image and what is the bounding box. So bounding box is basically a box that goes on top of the image and tells you where the drone is in the image. And then we're gonna train the YOLO version 8 algorithm. And after that, we're gonna apply auto distribution methods. So what methods did we use? We used for our baseline, we used the native confidence that comes with the algorithms. As we will see in the next slide, it performed the worst out of all. We used maximum softmax probability, or to be more specific, we used a temperature scale maximum softmax probability. So what is maximum softmax probability? Quick explain what are logits. So logits are basically the output of the algorithm, and in our case, because we have 3 classes for the in distribution, we got 3 values for our output. And the maximum softmax probability basically does is that it's taking the best out of them and creating a very massive separation, which is good for neural network. But in our case, what it will do is that it's going to make even auto distribution images to be very high in confidence about it. It will actually say that is 80% sure that this is one of the images that it knows, and it's really hard to see whether it is actually an in distribution or auto distribution if everything is really high confidence. So what the temperature scale does is soften the separation a little bit, and that way you can get a weaker confidence for auto distribution. The energy one, so instead of making the separation for each of the class, it looks on the sum of the logits. So when we have the 3 logits together and we apply sum on them, it's going to have the in distribution class way above the others, and the others are going to be really negative. But in auto-distribution case, all of them are going to be very similar to one another. So they found out that when you look on some of it and apply also a temperature on it to kind of soften it a little bit, you're going to get really good separation. And we also implemented a method that uses the Malanobi distance. It's different from the other. It's basically looking at the backbone of the algorithm and extract the final layer of the backbone. So in our case, we are getting a 256 vector, which is the feature space. And what it does is first, it applies all of the in-distribution that it's been trained on, and it's generating the mean of all of these vectors. And when it gets a new image, it's getting the vector of the new image and trying to see the Malanobi distance from it to the mean of them. But we didn't get good results on it, and I'm going to discuss it in the future work. But in the later slide, we are only going to refer into the MSP and energy because we get the best result from them. So the results, I will start with the detection results. So this is in the first bullet. So both resolution, the 640 and the 2024 were pretty high detection. So what is MAP50? It basically says that the algorithm is going to generate a bounding box. And when it's generating a new bounding box, it will compare the new bounding box to the one that it has on the validation test. So when it overlap above 50%, it's going to be a success. So 0.929 means that 92.9% of the images, the algorithm was able to detect the drone and put the bounding box on top of it, overlapping more than 50% of it. And we see that in 1024 pixels, on 1024 pixels, we actually get a better results, which is pretty obvious. What is the surprising is even on lower resolution, we got good results. I think that if you go back to the image that we saw, most of us can see that there is a drone in the sky. But what we found out on our evaluation, that it was not that good of auto distribution. So when we zoom up in lower resolution, it could see that this is a drone, but it had really hard time to validate if it's an in distribution or auto distribution. So here on the right, we have the auto distribution results. So what AU/ROC means. So what it means is that how much too positive you have from your whole evaluation. So when you getting an image and you said that this is in distribution, you're gonna look at all of this in distribution, what the algorithm said that this is in distribution, and you want to see how much of it really is in distribution. So for example, 1 means that every image that the algorithm told us that this is in distribution are actually in distribution. 0.5 means it's basically kind of the lowest results that we can get, but 0.5 mean it's basically random, so could be by 50% in distribution, so it's like flipping a coin. And when we look on the left values, that this is the 640 images, we get the results. So the native confidence was pretty much random, but we got pretty good results with the maximum softmax probability and the energy probability. But we get a much higher results on the far right of the graph, that this is 1024 and 1024. So we got way above 90%, which is pretty good for auto distribution. In this case, which is near auto distribution, and they basically look very alike. We also got surprising results. So in the middle, it was kind of a mistake that I made. So after I trained the 2024 algorithm, I kind of ran the same auto distribution that I had. So in the right, you can see train 124 and evaluate on 640. This is kind of a mistake that I made, but is really interesting. But it means that even when you trained a good algorithm, when you evaluate a lower resolution, it gave you worse results than training on the same resolution. And I think the most surprising was when I trained on 640 and gave it a high resolution images, I got the worst result that I get. When we looked in the logit, what we found out is that the algorithm kind of like took the in-distribution, and it was really sure with high confidence that this is a specific in-distribution type. So this is really interesting. So future work, I think the next step should be validate the on-real drone imagery. So it's called the sim to real gap, and it's a very hot topic right now. We need to add more UAV types, poses, and weather conditions. So why we think that the Maranobi didn't perform well, that when we look at each of the vectors, what we saw that it's kind of classifies them in the poses. So each pose is going to be treated differently. So we need to add this value to our tests. And thank you. Thank you for listening.
Hello, this is Captain Isaac Patterson. My thesis is titled A Framework for Mapping Attack Drone Operator Competencies to Simulation in Marine Corps Training. This research focuses on how the Marine Corps can better structure and evaluate simulation-based training for attack drone operators, specifically first-person view or FPV systems. As attack drone employment continues to expand across the FMF, units are looking for scalable and repeatable ways to train operators effectively. This research explores how we can connect the competencies operators need with the simulations available today. This presentation will begin with some background on attack drone employment and the training problem that motivated this research. We will then discuss the problem statement and research questions. Following that, I will discuss the research approach, including task selection, KSA identification, decomposition, simulation analysis, and evaluation. And we will then cover results, future work, and conclude with discussion. Starting with a little background, an attack drone in the context of this research refers to an unmanned aerial vehicle that transmits real-time imagery to an operator wearing FPV goggles or a helmet display. These systems are often equipped with ammunition and employed as a one-way attack weapon system, capable of delivering precision effects at tactical echelons. Recent conflicts, particularly the war in Ukraine, have demonstrated the rapid evolution and tactical relevance of FPV attack drones. Within the Fleet Marine Force, attack drone employment is expanding rather quickly. Units are actively experimenting with tactics, techniques, and procedures while simultaneously trying to build sustainable training pipelines. Live training presents several constraints. These include limited drone inventories, range restrictions, weather impacts, and the recurring costs associated with attritable weapon systems. Because of these limitations, simulation presents a potentially scalable pathway for attack drone operator training. The challenge is determining how to systematically connect these training requirements with the capabilities of available simulations. Currently, many FPV operator training simulations exist. However, there is no structured framework for mapping operator competencies, what needs to be trained, to the simulation environments available. How can those competencies actually be trained? To address this problem, the research focuses on two primary questions. First, how can a taxonomy of knowledge, skills, and attitudes, or KSAs, for FPV tactical employment be structured to support progressive training design and proficiency development? Second, how can simulation environments be systematically evaluated and mapped to those KSAs in order to guide the selection of appropriate training aids? This research uses a design science research or DSR methodology. The primary goal was the creation and evaluation of a practical artifact, in this case, a framework for mapping operator competencies to simulation capabilities. The process consists of several phases. First, task selection. Second, KSA identification. Third, KSA decomposition. Fourth, simulation analysis. And finally, simulation capability mapping. For task selection, tasks were chosen from NAVMAC 3500.107 Delta, which is the Unmanned Aircraft Systems Group 1 and 2 Training and Readiness Manual. Attack drone operator training was scoped into 4 general categories. The first being basic flight control and maneuver. Tasks related to this category are entry-level flight and drills associated. The second stage of operator training, individual tactical employment. Tasks related to this stage include basic target engagement at the individual level. The third stage of attack drone operator training, small team tactical employment. These tasks involve the employment or the use of a spotter UAS to conduct reconnaissance, transmit target location to the FPV drone operator, and conduct target engagement. And the final part of attack drone operator training was employment in support of offensive and defensive maneuvers. Tasks associated with this part of training are related to planning and coordinating attack drone strikes in support of a maneuver element. These selected tasks were organized within one of these 4 parts to support a progressive training development or a crawl, walk, run training development. Once the appropriate tasks were selected, KSAs were mapped to individual performance steps for each task. The goal with this phase was to identify the most important competencies required for successful task execution. Each competency was categorized as either a knowledge, skill, or attitude. After identifying KSAs, selected competencies for a single representative task were decomposed further. The example task used in the framework was deliver a hasty line of sight static strike. This task is located within the second part of attack drone operator training, individual tactical employment. For each KSA associated with that task, the framework identified the required performance measure or metric, the environmental cues and affordances needed for training, and finally, the feedback necessary for skill development. This decomposition process was important because it translated abstract competencies from the last phase into measurable and observable training needs. These needs can then be directly compared against simulation capabilities. This phase involved analyzing available simulations. The analysis focused on whether simulations could support the required performance measures and training needs identified during KSA decomposition. Simulations analyzed included liftoff and trip FPV, which are commercial simulations available on Steam, Dart FPV, which is a vendor company vigilante that has developed an FPV sim for the Marine Corps, and finally, the Virtual Drone Collective Trainer, or VDCT, which is an FPV sim developed by the Army's Combined Arms Center Training Innovation Facility, and it's built to run within VBS4. For this analysis, each simulation element was assigned a score of 0, 1, or 2. A score of 0 meant that the training element was not present within the simulation. A score of 1 meant that the element was present, but only through observer designation or manual assessment. And a score of 2 meant that the element was automatically captured or assessed by the simulation. The scoring system provided a structured way to compare the simulations and evaluate how effectively they supported training this identified TNR task. After simulation analysis, the framework mapped analyzed tasks and performance steps to each simulation environment. The purpose was to communicate how effectively a simulation could support training the identified TNR task. This phase uses a color-coded assessment approach. Red indicates that the simulation does not support that performance step. Yellow indicates partial support of that performance step, and green indicates full support for both the performance metrics and training requirements of that performance step. This mapping process provided a visual and structured way to evaluate training gaps and identify strengths, weaknesses of each of the analyzed simulations. After constructing the framework, it was evaluated by subject matter experts across the attack drone community. Subject matter experts reviewed the framework and provided their structured feedback. Participants were briefed using a standardized presentation and completed a feedback questionnaire. This group of participants included training designers, attack drone instructors, and attack drone operators. The evaluation collected both quantitative and qualitative feedback. Quantitative feedback used a 1 to 5 rating scale, while qualitative feedback allowed participants to provide recommendations and observations in written form. SME feedback was used to assess, first, the validity of the KSAs, were the right competencies identified, second, the accuracy of the simulation mapping, and third, the practical utility of the framework for training design. The results from this evaluation informed recommendations for framework refinement and future development. The results highlighted several important findings. First, no simulation analyzed fully supported training for the selected task, deliver a hasty line of sight static strike. Second, in most cases, simulations required a significant external augmentation in order to meet the identified training needs for the selected task. Feedback on the overall framework from subject matter experts was generally very positive. Participants agreed that the framework was useful for developing progressive training pathways for attack drone operators. Several recommendations for refinement also emerged during evaluation. These included clearly defining KSAs during the identification stage, considering competencies related to loss of signal or video while flying the drone, including KSAs related to payload employment and munition handling, identifying what declarative knowledge is required before conducting basic flight training, evaluating each simulation for their scalability and integration into broader simulation federations, and finally, applying the framework to a larger set of candidate simulations. Overall, the results suggested that current FPV simulators provide value for basic flight skills, but they still require substantial augmentation to support tactical employment training. Recommended future work consists of continuing development of the framework across the full range of selected attack drone operator training tasks. Additional work includes applying the framework to all candidate simulations currently being tested or fielded by the Marine Corps. And finally, exploring attack drone employment within the broader context of Marine Corps fires integration and combined armed operations. Thank you for your time today. I look forward to your questions and discussion.